Absolute accuracy, direct hits on the vital points in the target area. This must always be the primary objective of the bombardier. But on many bombing missions, enemy opposition has proved that accuracy can be expensive, and precision bombing can be completely successful only when the mission is accomplished at a minimum cost in ships and men. To this end, these two computers have been adapted to a new use in high-level bombing procedure. Through the use of either the E6B or the A.B.C computer, preset sight data can be computed without any change in the ship's course. Drift and dropping angle may be determined and the release point established for any attack heading. Since either computer may be applied to the bombing problem, we will discuss each one separately. In this procedure, the E6B computer is used to solve for drift and dropping angle and convert these factors into a true element which will be constant on any compass heading. It will first be necessary, however, for each bombardier to modify his E6B index card in the manner shown here. Notice that this particular card specifies the M38A2 practice bomb and the 12,000 to 15,000 foot altitude bracket. A complete set of cards must be made, one for each type of bomb and for each altitude bracket. Here is the method by which these cards are prepared. First, consult the standard ordnance bombing tables and find the dropping angles for the various altitudes and ground speeds. In using Norden equipment, it will be more convenient to express degree of dropping angle in terms of tangent value. So convert degree to tangent by consulting either your table of natural functions of angles or the Norden sight quadrant. Then make up a new bombing table which will show that for each combination of ground speed and altitude, there will be one particular tangent value of dropping angle. And finally, since the E6B index card is already calibrated in ground speeds, it becomes a simple matter to write in the various altitude columns, each with its corresponding list of tangent values. It will now be possible to read any given altitude and ground speed and quickly determine the correct tangent value. Obviously, when using the E6B solution with Sperry or other dropping angle sights, the index card should be calibrated in degrees of dropping angles rather than in tangent values. In solving a problem with the E6B, the tangent value for any one altitude is to be considered constant along its entire ground speed line. This line also represents other tangent values under their corresponding altitudes. Degree of drift is measured in the normal manner using either the right or the left side of the center line, as the case may be. The several steps in the E6B procedure may best be explained by applying the computer to this theoretical problem. We'll assume that the altitude over the target will be 15,000 feet. The indicated airspeed, 160 miles per hour. Temperature aloft, minus 20 degrees centigrade. The type of bomb, M38A2 practice, and the attack heading, 105 degrees. First, the computer index card should be checked to see that it agrees with the type of bomb in the load and specifies the correct altitude bracket. Next, we'll determine true airspeed in the usual manner. In this case, we find it to be 200 miles per hour. Now, reversing the computer, the transparent disc is centered over this true airspeed figure where it appears on the index card. Next, the ship's present heading is established. For the purpose of the problem, we'll assume it to be 40 degrees. This heading is set up on the E6B compass rose. It will now be necessary to establish drift and tangent values for the present course. To do this without making a change in heading, the secondary clutch on the sight is left engaged and the directional clutch disengaged. The bomb sight is then used as a drift meter. The fore and aft hairs are tracked across the ground, moving always in the same direction until all lateral movement stops. Then the telescope is clutched in. The scope index is started from a point near the middle of the quadrant and allowed full travel, for apparent motion becomes more evident as the index nears the zero dropping angles. Now, with the sight properly synchronized, drift and tangent readings are taken. Let's assume that the tangent reading in this case will be 0.65 and the drift reading 7 degrees right. To transfer this data to the E6B index card, the proper altitude column is first located. In this case, it will be 15,000 feet. Then, under this column, the 0.65 tangent line is established. Next, the drift reading is set in by tracing a drift line at 7 degrees right of center. Now, where the drift and tangent lines intersect, a key point is marked on the disc. This point will be used to compute further drift and tangent settings for any change in compass heading. Finally, a wind vector line is drawn from the key point to the center of the disc. By rotating the compass rose, the wind vector is superimposed over the center line, and wind direction and velocity can now be read. Here we see the wind is blowing from 268 degrees at a speed of 40 miles per hour. Or as we see it here, the difference between 200 and 160 miles per hour.